All right. So back into the flow of things, and we're beginning our conversation on inferential statistics. We had previously been talking about descriptive statistics, but now we're stepping into inferential statistics. And in particular, the way we're making this transition is by going and talking about probability and probability distributions. So that's the particular way that we're making this transition into inferential statistics. So, what have we done before? We've collected, organized, and presented data. So, we've done all three: collected, organized, and presented the data. And we are answering the question of now what? What do we do now? Right? So, inferential statistics, if we go back to our analogy where we are cooking some big pot of chili or a big bowl of soup or something, and we want to find out if we need more salt, so to speak, right? The first step, the first thing we would do is actually take a spoon out. We got to take a spoon out for us to be able to taste it. So we would take the spoon out, and that process of picking out a spoon is sampling, right? We're not going to just scrape the bottom part, right? We need to mix it up a bunch so that our spoon is representative of the entire pot. And after we take our spoon out or sample, we're going to taste it and describe it. And when we taste it and describe it, that's basically like the descriptive statistics part, where we're not necessarily saying what it needs, we're saying what it tastes like, right? We're not saying what it needs. But the next part, which is the inferential statistics, is us saying, what does the spoon that we just tasted tell us about the rest of the entire pot of soup or chili or whatever it is. It's an analogy with a spoon. We're taking a spoon, and we're going to learn about the whole pot of chili from our single spoon. That is the best drawing of a spoon I could do. So the basis of that inferential statistics is probability, right? That's the basis of it. And basically, with probability, we're looking at the likelihood of something occurring or happening. Right? How likely is it that something happens? That's what we're looking at. Right? Is it very likely? Is it not so likely? Right? That's what we're looking at. We've all kind of done probability in some way in our lives. Usually, it may not be super mathematical the way we do it, but we have done probability in some way. Now, when we're looking at probability is always going to be between 0 and 1. And when we have something that is more likely to occur, the probability will be closer to 1. And when something is less likely to occur, the probability will be closer to 0. Right? And when we do probability, the nomenclature, or like the way we write it, is we write this, like this function notation. And this means the probability of event A, or we could say P of A, or the probability of event A, where event A is just whatever thing we're trying to find the probability of, right? And the second one just tells us that probability is a mathematical representation of us saying that probability is between 0 and 1, right? Sandwiched in between them. So question, what if something was going to happen every single time? It was almost certain to happen. What do you all think the probability of that thing would be?
One.
1. And if something was never going to happen, what would the probability of that thing be?
Zero.
0. And if something happens about half of the time, what would you guess is the probability?
Like 0.5,
One.
like
One.
Will we still consider it zero?
0 to
Nope.
1.
The
Or zero or half?
it would be about 1/2. If something was going to happen about half of the time, its probability would be about 1/2. Right? That's basically like what probability is saying about how many times is it going to happen out of all of the things that could happen. So to find probability, there are two main ways that we're going to utilize. Right? We have what we call the theoretical approach, and we'll also be looking at the experimental way. Now, both of these methods are almost exactly the same like conceptually. The difference is that when we look at the theoretical approach, we haven't actually done an experiment. When we look at the theoretical approach, we're saying how many possible favorable outcomes. Favorable just means it's the outcome that we want, and we're dividing by the number of possible outcomes, right? So we're saying how many favorable outcomes divided by the total number of possible outcomes, right? So if we wanted to flip a coin, let's say we wanted to flip a coin and we wanted to know the probability that we get heads. How many how many ways or favorable outcomes are there where we get heads if we flip a coin? There is only one. Only one way for us to get heads when we flip a coin. And how many possible outcomes are there? There are two. We could get heads or we could get tails. We could get either one. We could get heads or tails. Right? So either of those are possible outcomes. So the probability that we get heads from a theoretical standpoint is 1/2. Does that mean that every time we flip a coin, right, if we flip a coin, we're going to get heads, then tails, then heads, then tails? No, it doesn't mean that. Does it mean that if we flip a coin 10 times, we'll get 5 heads and 5 tails? No, it does not mean that. What it means is that theoretically, when you flip a coin, getting heads is just as likely as getting tails, right? Now, let's say we were to flip a coin 10 times. If we flip the coin 10 times, and the first time we got tails, second time we got heads, then we got heads again, we got tails, then we got heads, we got heads, we got heads, we got tails, we got heads, we got tails. I believe that's 10 times. The experimental probability formula is when we actually do an experiment and we say how many times did the event that we want occur. So how many times did we get heads in this experiment? How many times? Anybody?
6.
6 times. And how many trials did we do in total? How many times did we run the experiment?
10.
10 times. Right? So this time we got 1/2, which, just to be clear, is 5/10. So we can write them in a similar way. Right? So we have 1/2, which is 5/10. Right? And we have 6/10. Notice that our probabilities were not the same. Y'all notice that? Anybody notice that? We're doing the same thing. We're measuring the same probability. Notice that they're not the same. If we wanted our experimental probability to be closer and closer and closer to this theoretical probability, anybody have an idea of what we could do? What could we do if we wanted that to happen? If we wanted to make our experimental probability get closer to the theoretical probability. Any ideas? I need an idea from somebody.
Will we possibly take one away, or?
So taking one away, that wouldn't do it. What if we did 100 flips? Do you think that would make it more likely to be 50-50 versus only doing 10 flips?
No.
Possibly, yeah.
Okay, well, let's hold this thought. We're going to come back to it in like 1
So
second.
Professor, it would need to be equal.
For it to be 50-50, yeah, we would need to get exactly the same number of heads as tails, right? That would.
So then we would. So for your question, because I was still writing something. So the event occurrence would be equal to the number of trials.
No. So the number of times the event occurs is how many times we get the outcome that we want.
Okay.
And the number of trials is how many times we just do the experiment at all. The question was, how could we get this probability, which is one way of saying the probability we get heads, because we did an experiment and our experiment told us that 6 out of 10 times we'll get heads. But when we theoretically just think about the probability of getting heads, we know it's 1/2, right? That's the probability theoretically of getting heads. So we're going to hold that thought. We'll come back to it in a second.
Okay.
So what we just looked at was like called the frequentist interpretation. And that frequentist interpretation is basically where we're looking at probability as a proportion, right? Where it's a proportion. A proportion either to the number of ways that something can happen versus the number of things that can happen, or a proportion of the number of ways we observe something to the number of times we made an observation, period. Right? So that's the frequent. We're basically saying how frequent is something happening, right? That's basically what we're saying. How frequent is something happening? The other main approach to probability that we won't necessarily go through too deeply in this class, but is the Bayesian interpretation. And basically what that is kind of looking at probability in a subjective manner, right? And it may seem odd to do math and statistics from a subjective manner, but computers and stuff are getting so good that they can kind of make connections between things that are seemingly not connected, that we wouldn't be able to necessarily make connections between, right? Because they can process so many different things. But again, mainly, we'll be looking at that frequentist interpretation, which is basically saying a comparison between how many ways something can happen, right? And, how many possible things actually do happen. Now, when we look at probability and measuring probability, in general, we're talking about what we call random processes, right? And random processes are basically where we know what events could happen, but we don't know what's going to happen, right? You know what could happen, you know what possibilities there are, but you don't know what's going to happen. So like for our coin flip, we know that when we flip a coin, we can only get heads or tails, right? But we don't know which one we're going to get. We don't know if we're going to get heads. We don't know if we're going to get tails. Sometimes it's helpful, even when something is not random or truly random, it's helpful to model it as random, right? So, for example, you may treat, like if you put your Apple Music or whatever, I don't know if anybody had music libraries anymore, but if you put it on shuffle, right, you may treat it as random if you were doing some kind of, experiment with it or some kind of statistical analysis, even though it would not really be random, right? So back to our question, and this puts it kind of in a different perspective, I think. Look at these three different events, and the question is, which one would surprise you the most? So we flip a coin 10 times and we get exactly 3 heads out of our 10 coin flips. The next one is we flip a coin 100 times and we get exactly 3 heads out of the 100 coin flips. That means 3 heads and how many tails? 97 tails. And then the last one is we get exactly 3 heads when we flip a coin 1,000 times. Which one of these 3 things would be the most shocking? Which one?
C.
C, right? If we flip the coin 1,000 times and we got only 3 heads, that leaves us with 997 tails. Could you imagine? Like, I would just go play the lotto if something like that happened, right? I would go play the lotto because that's just like weird luck, right? If you flip the coin 1,000 times, about how many heads are you expecting? How many times would you expect? Like, if you had to make a guess, how many times would you expect to get heads?
At least half of the time.
Which would be how many?
One.
It's 1,000 coin flips. What's half of 1,000?
500.
At least 5. Like,
yeah, we'd expect to get like 500 heads and 500 tails, right? That's what we would expect, or something close to that. Something like 497 and 503. That wouldn't be shocking, right? 490 and 510. That wouldn't be shocking. But 3 heads and 997 tails, that's crazy, because that would mean that you were getting streaks of like at least 300 tails in a row. Could you imagine flipping a coin 300 times and getting tails each of those 300 times? That's, I don't know, you'd be like, there's some kind of witchcraft going on. That's what you would say, right? So yes, that one would be the most shocking. And what that gets us to is what we call the law of large numbers, right? Theoretically here, we knew that the probability of getting heads or tails is 1/2. So we said we expect that when we flip a coin 1,000 times, it's going to be closer to 1/2 because things kind of balance out. And that's what the law of large numbers tells us. It tells us that the more times we do an experiment, the closer our experimental probability gets to our theoretical probability. So if you were to flip a coin 1 million times, right, you're more and more likely to get like close to a half, right? Close to a half. You're more and more likely to do that. And if you keep doing that 1,000,000,000 times, you flip a coin 1,000,000,000 times, you're like really likely to get 500 million heads, 500 million tails, or something that's so close, right, that it just makes sense. But if we flip a coin 2 times, you're not going to be shocked if you get heads, heads. If you flip a coin twice, if you flip a coin twice, you're not going to be shocked if you get tails, tails, and you won't be shocked if you get heads, tails, because you only flipped it twice. So the law of large numbers tells us that the more times we perform an experiment, the closer we get to the theoretical probability. The more times, the closer we get. So, question. Let's use the same theory. Let's say we have a coin and we flip a coin 10 times. And on each of the first 10 tosses, we get heads each time. We get heads, 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 heads. And the question is, are we more likely to get heads next, or are we more likely to get tails next?
Heads.
So Nakia says heads. Anybody else want to chime in? Are we more likely to get heads? If you're a betting man, you just went, you're gambling. You're like,
Hey,
what are you going to bet for? Because you just got all these heads. What are you betting? You betting that we're going to get heads again, or you betting we're going to get tails? I need to hear some answers. I heard people say heads. Okay. No one's going to be like, my hot streak is over. It must be tails next.
I would say tails.
Tails, okay. Chanel, I don't know what you're saying. I just see you mouthing things.
I was agreeing with you. I was saying the hot streak is over, tails.
Gotcha. Hot streak is over. Okay. So, in reality, the coin doesn't care what it got before, does it?
No.
No. So our
No.
probability doesn't change. For that next one, we're not more likely to get heads. We're not more likely to get tails. Still just half and half. It could be heads, could be tails. Neither is more likely. Because the coin doesn't have a memory. You know what I mean? Like, we didn't have a hot streak and now it's over, so it's due for a tail, right? And we aren't on some kind of hot streak, so it must be heads the next time. And what they call this gambler's fallacy, right? So people make mistakes a lot of times because they're playing, roulette or something, and they get black every time. And now they're like, oh yeah, it must be black the next time. Or they're like, oh yeah, I'm going to go on red this time, right? It doesn't work like that, right? There's no memory associated with a coin. There's no memory associated with a random process in that way. Now, when we're looking at outcomes or different events or things that could happen, we have two main types. We're going to start off by looking at what we call disjoint outcomes, and the other type is called non-disjoint outcomes. So with disjoint outcomes, also called mutually exclusive outcomes, these are outcomes that cannot occur at the same time. They cannot happen at the same time. On the other hand, non-disjoint outcomes can happen at the same time. So, question, if we flip a coin, can we get heads and tails at the same time if we flip one coin?
No.
No, we cannot. So would getting a heads on a coin and getting tails on a coin be mutually exclusive or non-disjoint?
Non-disjoint.
No. Mutually exclusive.
Mutually exclusive because they cannot happen at the same time, right? They cannot
Correct.
happen at the same time. Now, what about the probability that you get pizza and broccoli for dinner? Can these things happen at the same time? Are they mutually exclusive or are they non-disjoint?
Non-disjoint.
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 They can happen at the same time, right?
Right.
You could get pizza and broccoli for dinner. I mean, it's a weird dinner, but that's possible, right? They can occur at the same time. There's nothing that cancels them out, right? So let's look at this example. Here, can somebody read this for me?
What is the probability that a randomly sampled student thinks marijuana should be legalized or they agree with their parents' political views?
Exactly. So that's the question. What's that probability? So the first thing we need to do, right? First things first. What kind of table is this?
A pivot table?
Nope.
Frequency.
Nope. Starts with a C. A C. Extra credit for whoever gets it.
Huh?
Jeez. Contingency table? There's a contingency table. So as it is, we're looking at two different variables and we're comparing the results between the two different variables. And the way we're reading this, right? So this down here, and if we look horizontally, right, this direction, we're looking at the results for whether or not people think you should legalize marijuana. And if we look vertically this way, we're looking at the results for whether or not people share their parents' political views. So here, and then in the middle is like the different places of intersection. These are the places of intersection in the middle. So when we look here, if we wanted to say how many people share their parents' political views, how many people would that be? Look on the table. Find the yes.
78.
Not 78. You didn't go down far enough.
118.
118.
118, exactly. So this no corresponds to here. This yes corresponds to here. This no goes to that total, and this yes goes to that total. Right? That's where it goes. And all of the numbers in the middle, right? The numbers in the middle correspond to like the intersection between them. So which group of people, right? Which group of people are we looking at to say that they think marijuana should be legalized or they share their parents' political views? So that's what we need to find. Because again, we're going to do that kind of interpretation. And that interpretation is just going to be saying, well, how many people did we interview in total? Right? So total is on the bottom. And favorable outcomes will be on the top. Right? So that's what we need to find. What's the total? First, how many people did we survey in total?
165.
165. So that's a starting point. We know that 165 needs to be on the bottom. And then on the top, we need to figure out how many people were here, marijuana should be legalized, or how many people agree with their parents. So it's either or.
Well, is that now
118.
the 118
So the 118 would be what? How many people
favorable outcome?
share their parents' political views? So we could put that there. How many people share their parents' political views? 118. Now, who else is favorable? You're favorable if you share your parents' political views. You're
And
favorable if you
legalizing
do what?
marijuana.
Okay, so how many? Go ahead.
47.
Nope. 47 is not
114.
114. Yes. So that would be legalized marijuana. And then we need to take away some overlap, right? Because think about it almost like a Venn diagram type thing. These are the people that said yes, marijuana. These are the people that said yes, parents. Right? And who are these people? These are the people that said yes. Yes. Does that make sense? So to get how many people there are in total, we need to do this circle plus this circle minus this space in the middle, because that's the overlap. Minus that. So we did this circle plus this circle. That's the 118 plus what 114. And who is the space in the middle? How many people are in the middle that said yes, yes?
78.
78. So that's why we're going to do minus 78. And that will give us our probability. And we can see that the correct answer is B. That's the correct answer, B. Right? So that is how we would go through this. That's how we would look at it. And we could actually use this to find a bunch of different probabilities. And to start off, you're looking at how many ways can you get a favorable outcome.
So, Professor, I hear what you say. I mean, I understand. I see the way you did that formula, but for me, I felt it was a little misleading.
What do you mean?
Because when I'm looking at the contingency chart, because I don't know, I guess it's just not matched up like how I envisioned it. It should have been matched up with legalizing the marijuana and sharing the parent political views. It just seemed off to me because you went yes under for the 118, but then we go to the side the 114.
Yes, because remember what I said.
This
For
looks
contingency
off to me.
tables, look, it goes sideways like this. See all of that?
Mm-hmm.
Sideways like this. What you can almost do is almost when you start off, ignore what's in the middle.
Oh, okay. Ignore what's in the middle
Does that
and look at
look
the
better?
two outer totals. Okay.
You see the totals
two
now.
Outer, okay. All
now
right.
now I think it just kind of makes sense. Period, because you don't have the numbers in the middle. The numbers in the middle give you the
look at it.
overlap,
Okay.
right? So we still need to understand how to work with them, but the numbers in the middle, that's what they give us. They give us the overlap, right? Overlap between the different categories. All right.
Thank you.
So moving on, what we have here is a general addition rule. And basically the addition rule is for when we're looking at the probability of A or B, right? Probability of A or B. So that's what we were just doing. We did a or, either or scenario. And when we do the probability of A or B, this is the rule that we follow. We do the probability of A plus the probability of B minus the probability of A and B. Right? Probability of A plus the probability of B minus the probability of A and B. Now here's a note. If two events cannot occur at the same time, what kind of events did we say they were?
Disjoint.
They were disjoint events, exactly, right? Or mutually exclusive. So if they cannot occur at the same time, what is the probability that they occur at the same time? That sounds like a twisted up question, but if they
0.
Thank you, Nakia. Yes, if they can't occur at the same time, the probability that they occur at the same time is 0, because they can't occur at the same time. So if these two events are disjoint or mutually exclusive, we actually get this simplification where the probability of A or B is just the probability of A plus the probability of B, because this part here goes to 0, right? That becomes 0 if the two events are mutually exclusive, right? So it gets a little simpler if it is if our events A and B are mutually exclusive. It gets a little simpler. So really quickly, we're going to talk about what we call probability distributions. A probability distribution is basically where we want to list out two different things. We want to list out all of the possible events that can occur, and we want to list out the probability of each event occurring. So those are the two things that we want to list out, right? So in this case here, we're looking at the probability of the gender of one kid. We could get male, we could get female. Probability 0.5, 0.5, right? And when we have a probability distribution, one thing that's important is that all of our events must be disjoint, right? So they must be mutually exclusive. We cannot make a probability distribution if our events are not mutually exclusive. All of our probabilities must be between 0 and 1, and all of our probabilities must add up to 1. If they don't add up to 1, either we did our calculations wrong or we are leaving off a possible event, right? So we're leaving off something else. Because if we're listing out everything that could happen, right, all of those probabilities add up to every single possible thing. So the probability that one of these things happen has to be one because it's everything that could happen, right? There's nothing else that could happen. So every single time one of those things is going to happen. Here's an example of a probability distribution. We're looking at the gender of two kids. So we could have male, male, right? We could have female, female. We could have male then a female, or we could have a female then a male kid. And the probability of all of these are 0.25 because they're all equally likely, right? Neither of them are more likely than the other. So again, what are the two things that we're trying to list out when we do a probability distribution? All of the possible events and the probabilities that each of those events has, right? So let's look at this example here. So here's an example. So in a survey, 52% of respondents said they are Democrats. What is the probability that a randomly selected respondent from this sample is a Republican? Remember, if the whole probability of everything is 1, so if 52% said they are Democrats, what percent is Republicans? Anybody?
Can't use it with the calculate. I mean, using because the information's not enough information.
Why do you say it's not enough information?
Because 52% is Democrats.
Yeah, 52% is Democrats, but it's just this is Democrats.
Just talking about Democrats.
Yeah, it's no Republicans in this 52%.
No, but
unless
the question is this, right?
Mm-hmm.
Let's draw a little pie. Here's our pie.
I would say A, Professor, but okay.
So what we're saying is this: 52% are Democrats, right? 50% are Democrats. The question is, what percent are Republicans? What percent of the leftover? What percent?
So you're not just talking about the 52% as the sample. Like
we're not talking about the 52%. We
and to keep it at 1, we would say, is it A, Professor?
It's A, right? 0.48.
Okay, so y'all are saying to keep it at to make it all add up to 1, right? Anybody else have any insight? Anybody else have any insight? Any ideas they want to bring to the table?
These are our only two options, correct? Republican, Democrat. There's no independent party somewhere else.
I didn't say that. I didn't say that. The question didn't say that.
Well, it only talk about Democrats and Republicans. It don't say independent on there.
So if it's a whole pie of 100, you got 52%, it's going to be 0.48.
That's what I'm thinking, but I could be wrong.
Yeah, I could.
Well, you know what the truth is.
If we're not considering whether or not the question states it that other parties are possibly also included in this graph, then I would say less than 48%, because what we're assuming is that we're only counting Republican, Democrat. If there is in fact an independent party present, we cannot account for that number of people, so we can't make it 0.48, which equals the 1 if there's another party involved.
So that was a very good point as well, right? All these are good points, and that's the important question. We can't calculate it. So yeah, if there were only 2 possible political parties, then yeah, it'd just be Republicans and Democrats, right? Then it would be A, right? But some people might not even be. Some people might be independents. Some people might be libertarians. Some people might be in the Green Party, right? It's all these different parties, right? And people might be in different parties. So we don't have enough information because, again, right, what we did initially, we initially only made our sample space Democrats and Republicans. That's what we did initially. But we left off all of the other possibilities. So what we were trying to do was say Democrats and Republicans, so this must be 0.52. And since our sample space is just Democrats and Republicans, this must be 0.48, right? But we cannot say that because we don't know what else is left over. So it's a very important point when you try to make a probability distribution, you need to have an understanding of all of the different possible outcomes, right? That is one of the reasons why whenever you see these surveys and stuff, a lot of times you'll see that there's an other option, right? Because you just leaving, yeah, okay, maybe you only care about Democrats, Republicans, and independents, but because you don't want to overestimate or underestimate, you need to leave an option for people who don't affiliate with either one. So that's why you would put something like other, and that would be like a catch-all, right? Because there might be all kinds of different parties that people associate themselves with. So when we look at probability distributions, we also need to understand what we call the sample space, right? And the sample space is basically the collection of all possible outcomes. So it's again related to that Democrats and Republicans idea, right? But the sample space is all of the possible outcomes. So if a couple was to have one kid, right, what's the sample space for the gender of this one kid? It would be male, female. Yeah. That would be the sample space. But what if the couple had two kids? What would be the sample space for the genders of these two kids? Well, we could have male, male. We could have male, female. We could have female, female. We could have male. We could have female, male. Right? So that becomes our sample space. When we have what we call, complementary events, right? When we have what we call complementary events, we're talking about mutually exclusive events where the probability adds up to 1, right? So in the first case, we have 2 events, right? And the probability of both of these events adds up to 1. They are complementary. Basically, complementary means if it's not one of them, it has to be the other ones, right? That's what complementary means. So in the first one, male and female, those are complementary outcomes or events. But
so that's the same thing that you did with the heads and tails too, right?
It's similar with the heads and tails. Yeah, it has to be heads or it has to be tails. Heads and tails are complementary. And whenever the events are complementary, their probabilities add up to 1. Right? And if they are not mutually exclusive, they cannot be complementary. So if a couple had 2 kids, right? If we know that they're both not girls, what are the possible gender combinations? If we know that both of them are not girls, well, we could have 2 boys. We could have a boy and a girl, or we could have a girl and a boy. But these are basically the same, right?
Can I just say something right here, Professor, for a minute?
Yes, sure. What's
This
up?
is the kid. So, Professor, my whole thing is you doing the female and the male, and then the male and the female. To me, isn't that like the same? It's just one is before the other. Why would it still be counted twice?
So let's say, so there are some instances where we don't count it twice, where the order does not matter. But there are instances where the order does matter, right? So, I mean, even in this case, I think the order does matter because in one case you have an oldest daughter, but in the other case you have an oldest son. Those are not the same, right? Those aren't the same scenarios. I mean, those aren't the same households. Those aren't the same, situations. So in this case, the order kind of does matter, right? But in some cases, the order does not matter. So if it was just about, what are the genders, then the order would not matter, right? So, but in this case, it does matter because, yeah, I mean, it just depends on the framing of the question. But yeah, you are correct to point that out that, female, male, male, female sound like basically the same thing, right? And then sometimes we'll count them the same, sometimes we'll count them differently, depending on how the problem is stated.
Okay.
Now, what we need to talk about is what we call independent events. So if we have 2 processes, right, they are independent if knowing the outcome of one process provides no useful information about the outcome of another process, right? So let's say we played a game and we had in this game we had to flip a coin and roll a dice, right? If you flip the coin and get tails, does that now let you pick a different number or know what number is more likely on the dice to come up on the dice when you roll it?
No.
No.
No, it doesn't. Because what does the coin have to do with a die? Nothing, right? The coin and the die have nothing to do with each other at all, right? They have absolutely nothing to do with each other. So there is no, oh, well, I got a head, so that means it must be a 3, 4, or 5. That makes no sense. So flipping a coin and rolling a die would be independent events, right? Here's another example. When we flip a coin multiple times, all of our coin flips are their own individual processes. And all of those coin flips are independent because knowing what happens on one coin flip does not give you a better hint or a better idea of what's going to happen on the next coin flip. Right? So those would be independent. On the other hand, right? Or, well, what if we picked a card from a deck? What if we picked a card from a deck? What would happen? Would those be independent?
Yeah, because you want to know.
Would those be okay? So we pick a card. Let's say Chanel is our first person up. Chanel picks a card. I give her a card. Her card is a 2, and whoever gets an ace wins. Chanel just got a 2. Now it's Amila's turn to pick a card. Amila picks her card. She gets a 5. Right now it's Nakia's turn to pick a card. She picks her card and she gets a 9. When Shantae picks her card, is Shantae more or less likely to get the ace?
More.
Why more likely?
Because of all the other face cards they got.
Yes.
Because of all the other cards they got. Now the deck is smaller, right?
Yes.
The deck
it's
is
like
much
spades.
smaller. Yeah, it is like spades. Right? It's just like spades because you looking at what has already come out and been presented, so now you get a better idea of what else is left over in the deck, right? Just like spades. The only way that picking the cards, right, are independent is if we pick the card, like I give Chanel her 2, and then after I give Chanel the 2, I put the 2 back into the deck, shuffle the deck up, and when I shuffle the deck up, right, then I give the next person to let the next person pick. So now every time someone picks, it's 52 cards. Then it doesn't matter what you did. But if you pick and there's no replacement where you're not putting the cards back, you get more information because now you're less likely to get the next card. So let's look at this.
So is that like if you put on, say we playing Uno.
Yeah.
And the deck run out, we got to reshuffle and put them back with the colors.
Yeah.
Is that the understanding?
That would be a similar kind of idea. Yep, a similar kind of idea. Right, because once you replace the cards back in, right, it's like you're starting from a whole new deck. Right, so your odds aren't changing. So let's look at this example here where we can try to figure out how we can tell if events are independent. Can somebody read this for me?
So between January 9 and 12, 2013, Survey USA interviewed a random sample of 500 North Carolina residents, asking them whether they think widespread gun ownership protects law-abiding citizens from crime or makes society more dangerous. 58% of all residents said it protects citizens. 67% of white respondents, 28% of Black respondents, and 64% of Hispanic respondents shared this view. Which of the below is true? Opinions on gun ownership and race ethnicity are most likely. Professor, you want to take it away?
Yep, complementary or mutually exclusive or independent or dependent or disjoint. So that's the question. Which one of these is most likely? Well, let's start with disjoint because I feel disjoint. I don't know if that even makes sense in this context. You can be any race and have any view on gun ownership. There's nothing that stops those two things from happening at the same time. So we're going to cross that one out. What about mutually exclusive?
Isn't that the same as this?
It's the same
Oh.
thing. That was a trick
Yeah,
question.
that's
It's the
a-
same thing. So I was just waiting for somebody to say it, but yes, it's the same thing. What about complementary? Does that one make sense in this context? Remember, complementary means like if it's not this, then it's this, right? That's
No.
complementary.
No.
So if it's not heads, then
No.
it's tails, right?
No.
No, that doesn't make sense
Complementary.
in this context, right? So we're left with independent or dependent. So the question is basically, if you know somebody's opinion on gun ownership, will that tell you something about their race? Will that give you an idea of what their race would be? Or will
In
it
today's
not give
time,
you an
possibly.
idea? Well, no. We're not talking about today's time or anything like that. We're talking about the data that
You
we're
can't.
presented with here.
You don't know. You can't know.
No, you really
Look
In
don't
at the
that
know.
data
case,
that's
no.
presented here. So y'all have to do something. You have to separate what you think about the world from what the data in front of you is telling you. You have to separate those two things. So we're looking only at this data here. You have to forget everything else that you think you know about the world. Only look at this data. And this data told us that what percent of everyone said it protects citizens? What percent of everyone? We had 60, not 68. 58% of everyone said that guns protect citizens. 67% of everyone, of white people, right, said it protects citizens. 28% of black people said it protected citizens. And 64% of Hispanic people said it protects citizens. So the question is, looking at that information, do we have an idea? Are we more likely to know what someone's race is? Do we see differences in the? If it wasn't going to make a difference, wouldn't it kind of make sense that all of the percentages would be the same, right? They would all equal what? If there was no difference, they would all be basically 58% because it's 58% of everyone. So if they were all the same, then that would be 58%. But what we can see here is that it's not, right? Do more white people or black people believe that the guns in North Carolina believe that the guns protect owners?
More white.
More white people believe that guns. Is it a lot more or a little bit more?
A lot.
A whole lot more, right? What about black versus Hispanic?
Hispanic.
Is it a lot more, or you got to use some other adjectives in there, use some other words in there?
Also, there are a lot more.
Yeah, a lot more.
A lot
black.
more. What about Hispanic versus white?
It's not as much of a difference.
Not as much of a difference. Now, what about white and Hispanic versus everyone?
Highly populated.
What?
I mean, not populated.
It's more.
They the ones made up pretty much to everybody.
Yeah, that's almost everybody.
So
right
it's
there.
more,
That's,
right? 67%, 64% is more than the proportion of everyone, right? So a higher proportion of white people believe it, a higher proportion of Hispanic people believe it, and a lower proportion of black people believe it. So if you were a betting person and I told you that someone believes that guns protect citizens, would you bet that that person was a black person according to this data here?
No.
No, because that's
No.
the smallest number, right? If I told you that a person believes that guns make society more dangerous, would you bet that they were a white person?
We don't have the data.
Yeah, we do, because look at it.
Yeah.
It's an either or.
Say
Either
the question again, Professor.
we're asking.
Okay. Yeah.
If someone believes that guns make society more dangerous, are they likely to be a white person?
Yes, they could be. Yeah,
They could be white, but
if you compared them to the black, but
yeah,
they could be Hispanic as well.
They could be any one of them, but they're more likely to be one of these. which one are they more likely to be? They're more likely to be black in that case, because look at it. There was everyone who's not in this 28% is in the category of makes society more dangerous. So we're getting an idea that if we know something about gun ownership, we are likely to know something about race or ethnicity, right? That's the idea that we're kind of getting here. So would that make these two things independent or dependent? Knowing about one is going to tell us about the other. Is that independent or dependent?
Dependent?
That's
Independent?
dependent. Nope, that's dependent.
I think dependent.
Oh, dependent.
Yes, knowing about one tells us about the other one. That means dependent. So if we want to check for independence, this is how we check for independence. So when we want to say the idea of something being independent of each other, basically we're saying that we're trying to find the probability that if A occurs, right, we're trying to find the probability that A occurs given that B is true. Where A is one event and B is the other event. So that's what we want to find. The probability that A happens given that B, some other thing, is also true. Right? That's what we're trying to find. And the way we write that whole statement, A given that B is true, we write that like this. This is how we write it. P, I'm going to write it bigger so we can see exactly what I'm talking about. The probability that A occurs, this line means given that B is true. That's what we're talking about here. Right? And the thing is, if we're trying to check if two events are independent or not, right, we look at this statement right here. If the probability that A occurs, given that B is true, is the same as the probability that A occurs regardless of whether or not B is true, then the two events are independent. That basically means that A didn't really care what happened with B. The probability that A occurred did not change. Right? So if we look here back at that other scenario, we can kind of do a test. The probability that someone thinks that guns protect citizens is 0.58. Whereas the probability for each of these other ones, the probability someone thinks guns protect citizens given that they are white is 0.67. The probability that someone thinks guns protect citizens given that they're black is 0.28. Probability that someone thinks guns protect citizens given that they're Hispanic is 0.64. And what we can see is that these probabilities, they change once we add a different condition in there. Right? See, all these probabilities changed once we put a different condition in there. So that's what tells us that these things are not independent. Right? So we know that gun ownership and race or ethnicity are most likely dependent. Now, we can't just jump and be like, they're all 100% dependent, because we do have to like actually do some other statistical work. But that's the clue that it kind of puts us on. Maybe we have to do more samples, right? Something like that to kind of confirm our findings. There are other things that we need to do, this what we call hypothesis testing, where now we have this hypothesis and we do a certain kind of test to see if our hypothesis is going to hold true. So that's what we're saying here. Basically, after that, we would do a hypothesis test, right? And we would kind of look at, we do a hypothesis test. That's the main idea. We do a hypothesis test. So moving on. If we have independent events, we have what we call the product rule for independent events. So this is, again, for if events are independent, meaning that they don't care about each other. And if we wanted to know what the probability of both of the independent events occurring, right? So what's the probability that A and B occur? It's really easy. All we need to do is multiply the probability of A times the probability of B. What do you all think we would do if we wanted to find the probability that A, B, and C occur? What would we do? Anybody? A and B, we multiply probability of A times probability of B.
A times B times C, or?
Close enough. Probability of A times probability of B times probability of C. Right? So it doesn't matter how many events. If they're all independent, we can just multiply all their probabilities to find the probability that all of them occur. Right? That's what we can do. Multiply them all. So what would be the probability if we toss a coin twice? What's the probability of getting tails twice in a row? So let's draw some lines to represent our events. We flip a coin. What do we want the first time? Tails.
Tails.
And what do we want the second time? Tails.
Tails.
So the question is, what's the probability that this is our outcome? What's the probability that we get the first tails? 1 half.
1 out of 2.
What's the probability we get the second tails?
1 out of 2.
These are independent. They don't care about each other. So what are we going to do? We're going to multiply our two probabilities, and what do we end up with? We end up with 1 half times 1 half, which is 1 over 4. That's what we end up with. All right, 1 half times 1 half equals 1 over 4. So let's look at this scenario here. So a recent Gallup poll suggests that 25.5% of Texans do not have health insurance as of June 2012. And if we're assuming that the uninsured rate stays constant, what would be the probability of two randomly selected Texans both being uninsured? What's the probability that they both are uninsured? Well, we can do it just like our coins, right? Let's draw two events. We got an event here. We got an event here. What are we looking for the first one? That a Texan is uninsured. So I'm going to put TU for Texan uninsured for the first one. And what are we looking for the second one? Again, another Texan that's uninsured. Right? And what's the probability that the first Texan is uninsured?
1 half.
Nope, it's not 1 half. It's in this statement right here.
25.5%.
25.5%. But we need to put it as a decimal. That's an important note when we're dealing with percentages, and the percentages are
1 out of 25.5.
0.2.
Would it be?
Hold on. Let's take it one step at a time. So the probability the first Texan is uninsured is 0.255. What's the probability the second Texan is uninsured? The same thing. 0.255. Now we're going to multiply them by each other. When we multiply them, what do we end up with? 0.255 squared. Right? We could just multiply them out, but yeah, that's what we end up with. 0.255 squared. Multiplying the same thing by itself. Right? That's what we end up with. Now, here's the thing. Here's a question. So we're trying to compare what we call disjoint outcomes with complementary outcomes. So disjoint outcomes were outcomes that could not occur at the same time. Complementary outcomes were outcomes where it was like this or this. They're complementary. If it's not this, then it's this other thing. Those are complementary outcomes. So the question is, does the sum of two disjoint events, two events that cannot happen at the same time, do they always add up to 1? We have the probability of two events that cannot occur at the same time. That's the question. Can it add up to 1?
No.
No, it doesn't always add up to 1. I mean, it could, but it doesn't necessarily have to, right? That's like our Democrats and Republicans example. You can't be a Democrat and a Republican at the same time, but that does not mean that the only options are Democrats or Republicans. There could be other options. On the other hand, right, do the probabilities of two complementary events always add up to 1? Again, complementary is it's either tails or it's not tails. And those are complementary. Do they add up to 1?
Yeah.
Yes.
Yes, they would, because complementary means you have your event and you have everything that's not that event. You have the event and everything else. So that means it has to be 1 because it's all of. So like in that example, if we had said what's the probability that someone is not a Democrat, then yeah, it would have been 0.48 because everything else besides Democrat is not Democrat, right?
Hey, Mom.
Yes, you're not on
Mom.
mute. Not on mute.
I am so sorry.
No problem. All right, so moving on. You have just been memorialized in one of the lecture videos, Danita. All right, so moving on. Let's do another example. What if we were to randomly select 5 Texans? What's the probability that at least one of them is uninsured? Right. So in this case, if we were to randomly select 5 Texans, the sample space for how many Texans are uninsured, right? That would be 0, 1, 2, 3, 4, or 5. And what are we counting in this sample space? We're counting, right? We're counting how many of the Texans are uninsured. That's what we're counting. So if we have 5 of them, 0 of them could be uninsured. If 0 of them are uninsured, how many of them have insurance? All 5 of them have insurance if 0 of them are uninsured. And if 1 of them are uninsured, right, 4 of them have insurance and 1 is uninsured. Same thing for 2, 3, 4, or 5. So we're trying to find out what is the probability that at least one of them is uninsured, right? What, at least one. So we're interested in cases where at least one is uninsured. So which of these things would result in at least one of them being uninsured? It was kind of, showing it could be 1 of them uninsured. That's at least 1. 2 being uninsured is at least 1. 3 being uninsured is at least 1. 4 being uninsured is at least 1. And 5 being uninsured. Right? So all of these here are the same as saying at least 1. And then we have this example this one right here, which is 0, where none of them have insurance. That's the other side. So basically what we're trying to do is we're trying to break what was a more complicated sample space into a more simple sample space. And our simpler sample space is either no one is uninsured or at least one person is uninsured. So either no one is uninsured or at least one person is uninsured. So to solve this, what we would do, right, we're finding the probability of at least one is uninsured. We're going to, instead of going in the opposite direction, find the probability that one person is uninsured. Find the probability that 2 people are uninsured. Find the probability that 3 people are uninsured. And building up in that direction, since we have this 0 or at least 1, we know that all of the probabilities in this add up to 1, right? So 0 plus probability of 0 plus the probability of at least 1. Right? These are complementary, because if it's not 0, then it's at least 1. These must add up to a grand total of 1. That's what they must add up to. So what we can do to find this probability here, we can do 1 minus this probability over here. That's what we can do. 1 minus that probability over here. Right? So here, that's what we're going to do. What's 1 minus the probability that none of these 5 people are uninsured? And how are we going to do that? Well, we need to find the probability that one of them is uninsured. Okay. So what is the probability that a person would be uninsured? We know that the probability that a person was uninsured was 0.255, right? So what was the probability that someone had insurance? It would be 1 minus 0.255. And if we had 5 people, what would be the probability that all 5 of those people had insurance? Right? Or in this case, that no one is uninsured. It would be this times itself, dot, 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 times itself, dot, 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 times itself, dot, 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 5 times. Or basically 1 minus 0.255 to the 5th power. And that's what it would be, because we're multiplying it by itself 5 times. So when we go back here, that's where we got this number from. And then we're doing 1 minus that number. That's the probability that no one is uninsured. I'm sorry, that no one is insured. That's what this probability is. The probability that no one is insured. And we're doing 1 minus that number. And that's what we end up with. They just simplified it a little bit. Let me get 1 minus 0.23. You can do this in your calculators follow along doing the calculators. That's fine. And then you end up with a probability of 0.77. 0.7 being the probability that at least one person is uninsured. Okay? So same concept that they did here. We're going to skip past this example, but I encourage you to actually go through this example and try to do it yourself at home. The answer is in here. So try to do this example yourself, try to walk through it yourself, and try to see if you can figure out how to do it. So now we're going to really briefly talk about conditional probability. So conditional probability is basically like that same kind of given that. Probability of this given that this other thing occurs. We actually already did an example with conditional probability early on. That was like one of the first things that we did. Right? Was an example with conditional probability. Sorry. So here we have an example. We're going to use this contingency table to kind of work through this example. So it says researchers randomly assigned 72 chronic users of cocaine into 3 groups. One group was a desipramine group, one group was a lithium group, and one group was a placebo group. And we recorded the results, right? So we're measuring, did the person relapse or did they not relapse? Question, how many people did we survey in total?
72.
72. So we surveyed 72 in total, right? And how many people in total relapsed?
48.
48. And how many people in total did not relapse?
24.
24. And how many people took desipramine?
24.
And how many people took lithium?
24.
And how many people took the placebo? 24. Awesome. So the first question we have here is, that went too fast. What's the probability that the patient relapsed? Right? And they already circled the stuff for us. But what do we need to do? Again, we're doing that same kind of theoretical, well, this one is not theoretical, I'm sorry, experimental approach, where it's like number of favorable outcomes divided by total. So which outcome, how many times did a patient relapse? We already had that highlighted, 48 times. And how many patients were there in total? 72 times. All right, so that's what we got, 48 divided by 72. Makes perfect sense. Now in this case, we're trying to see what's the probability that a patient received desipramine and relapse. What's that probability? Received desipramine and relapse. Well, we need to find the column, the circle where, or the number that represents what patients relapsed and got desipramine. That's what we need to find. And we can find that because that's right here. They did both. They relapsed and they got desipramine. Right? And that gives us 10. And then we do it over the total over 72. Very simple and straightforward. So when we have conditional probability on the other hand, right, where it's basically that same given that. So the probability of A, given that B is true, given that we know B, right, that's what we're looking at there. And to do that, we do the probability of A and B divided by the probability of B. Right? The probability of both of them happening divided by the probability of B. So let's look here. And the question that we have here is, what is the probability, right, that someone relapsed if we know that they were given desipramine? I was trying to find the probability that someone relapsed given that they received desipramine. So probability of relapse given that, the line means given that, they received desipramine. This is what we're trying to find. Right. So we need to say probability of A and B. What was the probability that they relapsed and got desipramine? Well, we did that the last time, right? That was 10 over 72. So probability of A and B was 10 over 72 divided by the probability of B. When we found the probability that they got discipromine, what was the probability they got discipromine? Well, no, we didn't. What's the probability that they got discipromine? Look at the chart. How many people got discipromine divided by how many people there were in total? You're on mute, Chanel. But you rap, yeah. But yeah, you're on mute.
I was just wording it out. You said how many people got discipromine, which is 24.
Yes.
Over how many people total?
Yep.
72, 24 over 72.
Exactly. So you're 24 over 72. Right? And this, when we simplify this, we get 10 over 24. Now, I'm going to give you, the reason why it simplifies to do that is because the 72s are both in the bottom, and they're in the top and the bottom, so they both cancel. But you could do this all the way out, and you would end up getting the exact same thing. But the reason why I wanted to write it like this, 10 over 24, is because if we look at it carefully, look at what we're asking. We're saying if we know that the patient got discipromine, what's the probability that they relapsed? So if we know the patient got discipromine, do we even need to look at the people who got lithium or the placebo? No, we don't. So I'm just going to cross all of this out because we don't even care about these people right now because we're only looking at the people who got discipromine. So we can look at the total number of people who got discipromine. How many people in total got discipromine?
24.
24. And how many people out of those people relapsed?
48.
10.
So no, y'all are looking. Somebody was just looking at this total down here. We're not looking there either. 10 of those people.
10.
Exactly.
10.
And you notice what? These are the same numbers. So contingency tables kind of give us an easier way to find some of these probabilities because basically when we say to given that, it's like we know one thing, so we're eliminating all the other stuff. We're like filtering out all the extra stuff. And we're focusing on one of the variables or one of the things, one of the outcomes, right? Notice I didn't simplify them. The reason why I didn't simplify them, like I didn't change 10 over 24 to a decimal, the only reason why is because I want you all to kind of get that visual. Sometimes when you write the probability as a decimal, you lose track of what it is that you're actually dividing. Right, so
Yeah,
you can go back.
I know.
Say that one more time, Nakia.
I said, yeah, because I'm one of them. When you do the decimal, I get distracted. Thank you.
Yeah, so the decimal, I mean, you can always just do that last step. Go on your calculator, 10 divided by 24. Just like that. Very easy. Right, but it is useful to leave it as a fraction for as long as possible because that will let you kind of just see what is it that I divided and make sure you're dividing the right thing. Alright. So that's what we had here. Let's find some other ones. I'm going to go back to a blanker slide. In this one, ignore what's there so far. Just use the chart. Let's go all the way back. There we go. Let's go here. What is the probability here that someone who we know took the placebo, what's the probability if they took the placebo? What's the probability that they did not relapse if they took the placebo? That they did not relapse.
4 over 24.
Oh, super quick.
4 over 72.
Almost, Nakia. It's 4 over 24 because, again, we're ignoring all of the other stuff because we're only looking at the section that is the placebo. Right? We're only looking at the placebo section. So it's 4 over 24. Let's do another one. What will be the probability that someone, if we know someone relapsed, listen to the question. If we know someone relapsed, what is the probability that they took lithium? If we know they relapsed.
18 over 24?
Nope, not quite.
18 over 24.
Nope.
18 over 72.
Nope.
The 7.
Think again about the wording. The wording
18
changed.
over 42. 48.
There you go. Exactly. The wording changed. The last time It was us looking here because we were like, we know they took the placebo, so we're looking here. These are all of the people who took the placebo. But this time, what is it that we said we know? We know that the person relapsed. Who are the people that relapsed? These people here are all the people that relapsed. And then we're saying which people took lithium that relapsed. That would be 18 people took lithium and relapsed over 48 people who relapsed. Let's do another one. What would be the probability? Let's find this probability. I'm going to write it out this time. We're going to do P what would be that probability?
20 over 24.
Nope. That says no relapse.
4 over 24.
4 over 24. Yes, that would be 4 over 24. Who are we looking at? Well, the second one is the information that we know because someone took a placebo given that they did not relapse. So that's these people. No relapse. That's what we know. Probability they took a placebo, 4 over 24. Very good. When you all go back.
Okay, I see it, Professor. I gotta make sure I'm really paying attention to the chart.
Oh yes, okay. Yes. Probability is like that. You gotta be super attentive to detail. When you all go back and watch this video over again, as I ask each question, you should pause the video, right? Try to work it out yourself, and then watch what the solution is. You can also take this same chart and come up with your own probabilities. What's the probability that someone, took the placebo? Period. Right? Let's do that one. What's the probability that someone took the placebo? Notice there's no given, it's not conditional. What will be the probability that someone took the placebo?
And what we know is 24 total.
That took the placebo, yes. So what will be the probability?
24 over the whole thing is 72.
Exactly, 24 over 72. All right, very good, very good. All right, what will be the probability? Let's see who's paying attention. That someone took disipramine and lithium.
48 over 72.
Nope, not quite. Let's see who's paying attention.
24 over the 20.
If they took both disipramine and lithium?
Yes.
So we're not calculating the total of each
24
that took.
Oh, so 24 plus or times 24 over the 72?
Nope. That they took disipramine and they took lithium. Chanel, you got to come off mute if you're saying something. Are you just speaking to yourself?
I was saying, did anybody do that though?
Did anybody do that? Was that an option?
Was that an option?
Reading the instructions on what happened with this focus group, or not the focus group, it's this experiment.
So, Professor, would it be 24 plus 24 over the 72?
Nope.
So what?
Listen to Chanel's question. Chanel's question is a guiding question right now. Did anybody do this? Did anybody take disipramine and take lithium?
No.
No one did that.
I didn't see it, but I thought you was creating it just now.
No, I'm not creating nothing. I just asked the question. So what would be the probability that someone took disipramine and lithium?
0 over 7.
0.
0.
So 0 then. Okay.
Right. Remember, if you have two events that are mutually exclusive, meaning they did not occur at the same time, the probability that they both occurred is 0. Right? It sounds kind of dumb, but what's the probability that something occurred that could not occur? It's 0, right? Let's change this slightly. Slight change. I'm going to change it from and, meaning they both occurred, and I'm changing it to or. What's the probability that someone took disipramine or lithium.
So that would be 48 over 72.
The 24 over the 72 twice.
Yeah, I think what both of you all said. When we do or, we add, right? So or we add, so we get 24 over 72 plus 24 over 72, so we get 48 over 72. Like that's how many people took lithium or discipline. Very good. Like y'all are quick.
And
Very
that's
good.
the one I thought you was trying to create for us at first, although we didn't have the actual data there. But you're right. That's teaching us how to, I guess, just look at what we got in front of us.
Yeah. So it gets a little tricky, right? It gets a little tricky. So we did these examples already. So in general, we have a general multiplication rule, right? We had done a multiplication rule before for if two events were independent, but we need a multiplication rule for if the events are not independent or if we think they're not independent. So if we think they're not independent, our multiplication rule changes a bit. Then the probability of A and B becomes the probability of A given B times the probability of B. Right? That's our new multiplication rule. Probability of A given B times the probability of B. Right? So moving on. We're gonna go past this one. We're gonna skip this example. But again, you can dig through this example a little more if you want to. So just as a kind of overview, right? Again, if the probability of A given B equals the probability of A, then events A and B are independent, right? Or basically B doesn't tell us anything about A. So that's just something to remember when you're doing these probabilities, right? Something to remember. So I'm gonna move on. So here's really quickly, this last part should take us like maybe less than 5 minutes. But if we're sampling from a small population, meaning that this is a really small population, we have two different ways of doing that sampling. We could sample with replacement. And when we sample with replacement, you put the thing that you took out, you put it back in. Right? So like our card deck example, you picked out a 2, you put the 2 back in before you go to the next person. So this will be an example of sampling with replacement. We have a bag of 5 red, 5 blue, and 2 orange chips. What's the probability that the first chip you draw is blue? Right? So we have 5, 3, and 2. Right? What's the probability that the first one is blue? Anybody?
2 out of 10?
Somebody said it?
Is it 2 out of 10?
2 over 10. So we want blue. Close, but they're not 2 blue chips. How many blue chips are there?
My bad, 3?
3.
There you go. So it will be 3 over 10. Right? Or 0.3. What if we did get a blue chip the first time? If we're drawing with replacement, what's the probability that we draw a blue chip the second time? If it's with replacement, meaning we picked out the blue chip, we put it back in. So the first time
3
we
out of
get
10.
blue. The second time we get blue. The first one is what? Somebody just said it. 3 out of 10. What's the second one? The same. 3 out of 10. Nothing changed. And we multiply, and what do we get? 9 over 100. Yep. I'm sorry. I thought we were I'm sorry. I scratched what I just said. I thought we were looking for the probability that both of our chips are blue. We're looking for the probability that the second chip is blue. So I think that was Gloria that said it. Who was it that said the 3 over 10?
I said it the second time, but I think Chanel said it the first time.
Gotcha. Okay. So yeah, for the second chip, right, because these two are independent, when we pick the second chip, the probability of the second chip is still just 3 over 10. But my bad, y'all. I just went like a step further, and I was like, what's the probability that both chips are blue? But that's not what we were doing. We were doing the probability that the second chip is blue if the first one was blue. And the probability is the same. It's like flipping a coin. Probability doesn't change no matter what we get the first couple of times. It still stays the same. Now, on the other hand, when we sample with replacement, right? I'm not on the other hand. When we sample with replacement, right? Similar kind of thing. And this was doing it with an orange chip, right? Now we get to the place where I was doing the problem. If we were sampling with replacement, what would be the probability of drawing 2 blue chips in a row? And this is with replacement. So the first one is blue. The second one is blue. Probability of the first one is 3/10. Probability of the second one is 3/10. And we multiply them, and we get 9/100. There we go. Which is 0.09. Right? We get 9/100, which is 0.09. Right? So that's our probability of getting 2 blue chips in a row. So moving on. When we sample with replacement, an important note, all of the times we pick out, they're all independent. But when we sample without replacement, they're not independent. So without replacement, you don't put the thing back. And what you notice that the probability for our second one changes. Because the first blue chip we had 3/10, but the second time, how many blue chips are left? We didn't put that blue chip back. Now there are only 2 blue chips. And when there are only 2 blue chips, right? How many chips are there in total? There are only 9 chips in total. So you see our probability changed. Right? It changed a bit because we took something out. So now our composition of our bag is different. So that would in turn change all of our other probability calculations. Right? It changes everything else. So I'm going to move on. An important note, when we draw without replacement, each of our draws are not independent. Right? And one important note is that when we have a really, really large sample size, like 10,000 or 1,000,000 or something, it doesn't really make too much of a difference because you might just be making a tiny little change. But when we have a small amount like 10, it makes a big difference between sampling with replacement and sampling without replacement. So we're going to move on really, really quickly past that. You could do this example on your own as well. And we are actually going to stop right there. We're going to stop right there. And we'll pick up with random variables in the next time. Next time we'll pick up with random variables.